is IP address. IP address stands for Internet Protocol Address, but what does this mean? Computers in Internet communicate with each other with underground or underwater cables or wirelessly. If I want to download a file from computer, then my computer should have an address so that other computer can find and locate my computer. Let us understand with others example. Like if someone wants to send you a mail, he or she should have your home address. Similarly, your computer should have an address. So that computer in internet can send you a file that you want to download. That address in internet terms is called IP address, which is nothing but the strings of numbers written in a certain format. IP address have two types, which is IPv4 and IPv6. So now I will explain about IPv6.
The main reason for migration from IPv4 to IPv6 is the small size of the address space in IPv4. In this section, we show how the huge address space in IPv6 prevent address depletion in the future. An IPv6 address is 128 bits or 16 bytes long, 4 times the address length in the IPv4. Computer normally stores the address in bit binary, but it is clear that 128 bits cannot easily be handled by several notations have been proposed to represent IPv6 and they are handled by the following show two of the notation, binary and color hexadecimal. The address space of IPv6 contains 2 to the power of 128 addresses. This address space is 2 to the power of 96 times the IPv4 address, definitely not address division. As shown, the size of the space is like the address space of IPv4. The address space of IPv6 is divided into several blocks of varying size, and each block is allocated for a special purpose. Most of the blocks are still unassigned and have been set aside for future use. One of the interesting features in IPv6 addressing is the auto configuration of hosts. As we discussed in IPv4, the hosts and routers are originally confirmed manually by the network manager. HCP protocol can still be used to allocate an IPv6 addresses to a host, but a host can also configure itself. Example, to allow sites to change the service provider, renumbering of the addressing prefix was built into IPv6 addressings. As we discussed before, each site is given a prefix by the service provider to which it is connected. If the site changes the provider, the address prefix needs to be changed. A router to which the site is connected can advertise a new prefix and let the site use the old prefix for a short time before disabling it. In other words, during the transition period, the site has 2 prefixes.
Okay, today I'm gonna talk about the IPv6 protocol. Okay. As IPv6 address is changing, it requires IPv4 packet format to change too. So the designer of IPv6 decided to implement remedies for other shortcomings now that a change is unavoidable. I will show you the other changes implemented in the protocol in addition to changing address, size and format. So this is IPv6 datagram. As you can see here, each packet, this is the packet of IPv6. Each packet is composed of base header, followed by the payload. Okay, this is the payload. So the base header occupies 40 bytes. This occupies 40 bytes, whereas payload can be up to 65,535 bytes of information. Yeah. So this is the base header. The base header has version, traffic class, flow label, payload length, next header, hop limit. It also has source address, which is 128 bits, same as 16 bytes, and destination address, also 128 bits, same as 16 bytes. So next, we're gonna take a look at the payload in an IPv6 datagram. So this is the payload. As you can see here, this is the base header. So this is the payload. It has next header length, extension header. So this is some next header codes. It has its own codes. So you can see here the codes. 00 is for hop by hoop option. 02 is for ICMP version 6. 06 is for TCP. 17 is for UDP. 43 is for source routing option. 44 is for fragmentation option. 50 is for encrypted security payload. 51 is for authentication header. 59 is for null, which is no next header, and 60 is destination option. So that's all for payload in an IPv6 datagram. So we go next to the extension headers. Okay, an IPv6 packet is made of a base header and some extension headers. Okay, the length of the base header, like I said before, is fixed at 40 bytes. However, to give more functionality to the IP datagram, we have to give more functionality to this datagram. This is datagram. We want to give more functionality, so we have to have the base header can be followed by up to 6 extension headers. Many of the headers are option in IPv4. So this is what I want to talk about. This is 6 type of extension headers that have been defined. Okay, these are extension header types. We have 6 over here. Like you can see, first is source routing. Second is hop by hop. Third, destination, fragmentation, authentication, and then ESP. So this is all for the IPv6. So this is all for the IPv6 protocol.
Comparison of network layer between version 4 and version 6. In version 4, it is one of the core protocols of standard spaces internet working method in the internet. IPv4 is written in decimal as 4 numbers separated by period. Each number can be up to 0 to 255. While the version 6 is the most recent version of the Internet Protocol, the communication protocol that provides an identification and location system for computers, network, and routes traffic across the Internet. IPv6 addresses are 128-bit IP address written in hexadecimal and separated by commas.
But in this video, we're going to focus on the ICMPv6 protocol, which is another protocol that has been modified in version 6 of the TCP/IP protocol suite. It is used by IPv6 nodes to report errors encountered in processing packets and to perform other internet layer functions such as dynamics. This new version follows the same strategy and purposes of IPv4. The first one is error message. It handles 4 types of error. The first one is destination unreachable. It should be generated by a router IPv6 layer in the originating nodes in response to a packet that cannot be delivered to its destination address. The second is packet to-bit. It must be sent by a router response to a packet that is cannot be forwarded because the packet is larger than the maximum transmission unit of the outgoing link, and incoming PBT must be passed to the upper layer process if the relevant process can be identified. The third is time exceed message. If a router receives a packet with a hop limit of 0, or if a router decrement a packet's hop limit to 0, it must discard the packet and originate an ICMPv6 time access message with code 0 to the source of the packet. Lastly, the parameter problems message. If an IPv6 node processing a packet finds a problem with a feed in the IPv header or extension header such that it cannot complete processing the packet, it must discard the packet and should originate an IPv6 parameter problem message to the packet source, indicating the types and locations of the problem. Informational message. The source address of an echo reply sent in response to a unicast echo request message must be the same as the destination address of the echo request message. The echo request and echo reply messages are designed to check whether the two devices in the internet can communicate with each other. Neighbor discovery message. Several messages in ICMPv4 has been redefined in the ICMPv6 to handle this issue of neighbor discovery. Some new messages has also been added to provide extension. The most important issue is the definition of the two protocols that clearly define the function of these group messages: the neighbor discovery (ND) protocol and the inverse neighbor discovery (IND) protocol. Group memberships messages. This responsibility is given to the multicast listener delivery protocol. MLDV1 is the counterpart to IGMPv2. MLDV2 is the counterpart to IGMPv3. This idea is the same as we discussed in IGMPv3, but the sizes and formats of the messages has been changed to fit the larger multicast address size in IPv6. Like IGMPv3, MLDV2 has 2 types of messages: membership query message and membership report message.
Hi, now we will continue to our next subtopic, transition from IPv4 to IPv6. Although we have a new version of the IP protocol, how can we make the transition to stop using IPv4 and start using IPv6? In the internet can move, the transition must be smooth to prevent any problems between IPv4 and IPv6 systems. So, the 3 strategies have been devised for transitions. One of these strategies can be implemented during the transition period. So the first strategy is dual stack. So this is for dual stack strategy. There are 3 layers: upper layer, IPv and IPv6, and underlying LAN or WAN technology. This way is for IPv4 system, and then this way is for IPv6 systems. Okay, next we will continue to our second strategy, tunneling. This is tunneling strategy. Okay, here is IPv6 host, and then this site is IPv6 host. At the middle of this host, there are IPv4 region. So IPv6 host is for IPv6 header, and then this sites also for IPv6 header, and at the middle IPv4 region, they have a tunnel. Tunnel provide for IPv4 header and IPv6. Next is header translation strategy. So this is header translation strategy. Okay, this site has IPv6 host, and this is IPv4 host. And then IPv6 host, we go to the IPv6 region and stop at the header translation here. So from this site, IPv4 host, we'll go to IPv4 regions, and then this is for IPv4 system, and go to the header translation and stop here. Okay. During the translation, a host may need to use two addresses, IPv4 and IPv6. When the transition is complete, IPv4 addresses should disappear. The DNS server you will learn in chapter 26. So the DNS server need to be ready to map a host name to either address type during the transition. But the IPv4 directory will disappear after all hosts in the world have migrated to IPv6. So we are done with chapter 9.